So the lesson one notes here, pretty simple. First we're going to talk about rocks and minerals. Well, rocks are a relatively hard, naturally occurring mineral material here. So this mineral material, what is a mineral? A mineral is an inorganic compound found in the earth. Inorganic means not from life. So if something has ever been alive or is alive right now, it's organic. Inorganic means not from life. In meaning not from life. So a pile of leaves can never become a mineral, but a bunch of sand can. So next in notes I have three different types of minerals to show you here. This first one, you can see how this is flaking off into a nice flat sheet. Well, that flat sheet, it pulls off like a piece of plastic. That's mica. Now mica is made of silicon and oxygen. So silicon, oxygen put together can equal mica, and that's a very common mineral here on the earth. The next one is feldspar. Now feldspar is made of silicon and sodium. Silicon and sodium make up feldspar. These are half the same, but they have very different properties just because this one has oxygen, this one has sodium. Quartz is pure silicon. Those are three really common silicon-based ones that we have here on Earth. And the rest of this notes packet here goes over the properties of minerals. Not a lot to write down, but this is basically this whole section. The 7 physical properties of minerals are that they have a crystal form, they have some sort of hardness to them, they have either fracture or cleavage. We have a whole lesson on that. Luster and color. Those are the different properties that make them up. Finally, their streak and their density are the different physical properties they can have. So the next units and lessons will go over these properties. So then here's lesson 2, crystals, fracture, and cleavage. We're going to go over all three of these. The first page talks about crystals. So crystals, a crystal is a solid formed by regularly repeating patterns of connected molecules. Okay, it's the regular repeating patterns that make up this crystal shape naturally. So for example, if we take a look at a couple of really common and popular crystals, we have diamonds. Okay, now diamonds are made from pure carbon. They're just straight up carbon. And if we look at what's inside of a diamond, we see a grid of carbon with carbon with carbon with carbon into kind of a square grid like this. Okay? These are really big quartz crystals over here. That's what these are showing. These are not diamonds. Anyway, the carbon is kind of interlocking like this. Okay? Now graphite is also made out of pure carbon. Okay, so they're made of the exact same thing, but their crystal shape is different. Okay? Graphite, the bonds are like this. Okay, there's still 4 bonds on every carbon, but the carbons, they're bonded with each other twice as much, and then there's this really weak thing holding the graphite together. Okay, so that would be how the crystal shape inside of diamonds is different than graphite. So the exact same thing, carbon makes up both of them, but just the way that the bonds between those carbon atoms line up makes something that's very, very hard and rare and expensive and awesome, like diamonds, and something rather common like graphite. So if you're using a pencil right now, what you're doing is you're breaking off sheets of this graphite and shoving little shards of graphite into your paper like splinters, basically. So as we saw before with mica, they break into little sheets. What's happening in this picture is that the razor blade was able to fit into the mica just by slipping in between those layers of silicon, kind of like this. So the razor blade was fitting between those layers. That's what's happening in that picture right there. So the last thing I need you to know about crystals is that there's a difference between when they cool fast and when they cool slow. So this takes time to get in order. So the atoms don't just magically get into these nice long lines. Okay, for something this big to form, it would take many, many, many years even to form. So there's a difference between fast cooling and slow cooling that I'm going to need you to understand. Now, fast cooling means that the atoms don't have hardly any time to get, in an order, into a pattern. So what we end up with is no crystals at all when there's fast cooling. The atoms are arranged randomly. And the example here would be obsidian. Obsidian does not have crystals in it. It's glassy. We'll see some in class. And the thing you really need to understand is that it cooled really quickly. If it's somewhere between fast and slow cooling, so it took a little while to cool off, you get small crystals. This is like medium cooling. Not fast, but not overly long. So these are small crystals you see inside of here. Now, slow cooling is the one that really kind of gets neat. If you have a long period of time, and these crystals have a long time where they can line up, what happens is you can have something huge, huge crystals. And so the atoms have more time to line up. And the example here is going to be Devil's Tower. Now, Devil's Tower, this was the inside of a volcano. So you have to imagine there's a giant volcano over this. And at some point, this was erupting. So this was a giant magma chamber. And this giant magma chamber was erupting for that last time, and it started cooling off. And over hundreds or thousands of years, all of those atoms had time to line up into gigantic crystals. So that they made crystals that you could see from miles away. So Devil's Tower is made up of many, many large, large, large crystals. Here's a closer view of the same thing. These crystals are so big. So big. This took a long time to make just because it cooled very, very slowly. So slow cooling means large crystals. On to cleavage and fracture. Okay, so cleavage, yes, it's cleavage. When the atoms line up such that the mineral breaks a certain way. So some minerals break in ways that are really distinctive and make them really easy to find. Okay, in our mineral kits in class, we'll see some that look like cubes and some that look like rhombuses. And that helps us see what they are. Those have what we call cleavage when the atoms break. So, for example, halite is the one that breaks into cubes. You start with a cube of halite. If you hit this with a hammer, you break it up, you're going to end up with smaller cubes. Okay? So it makes a cubic shape. That's not to say they're all perfect cubes like this, but it'll break in such a way that you'll still be able to say that it's trying to stay cubic. Okay, that means that the atoms are lining up in a nice straight way, and it's stronger, and it wants to break into these little smaller cubes. So that's an example. Halite is an example of a mineral that has cleavage. Okay. We're not going to go very much into it, but you should recognize cleavage. Cleavage in one direction means it'll just pull into a sheet, and we'll see stuff in class that looks like sheets. Feldspar wants to have cleavage in two different directions. So you'll see some planes, you'll see some flat surfaces in it. Halite, the cubes that we're talking about, that means it wants to break in three different directions. Okay, so you should at least be able to recognize cleavage when you see it. So yes, this has cleavage, this does, and this does. Okay, but if something doesn't have cleavage, it fractures. It does not have cleavage, so it fractures. The atoms do not line up. The mineral breaks up randomly with jagged edges. This is what you're familiar with. Okay? This just looks like regular old rocks and stuff like that. There's no straight edge to be found anywhere on these. So these are examples of fracture, but anything that has these nice flat edges, like this, or any of these, those have cleavage, and we'll need to use that to help identify them later on. That's the end of lesson 2. Okay, on to lesson 3, mineral hardness. So one of the key ways you can identify minerals with its hardness. So you could tell hardness is the ability to resist scratches. So if something is hard to scratch, that means it is more hard than something that's easier to scratch. Okay, so what we use in this is Mohs hardness scale. Okay, now you don't have to memorize the whole thing, but you should have a sense for this at least. Okay, the Mohs hardness scale starts at 1 and goes to 10. A 1 on the hardness scale is the softest mineral, which is talc. Okay, the example is talc. And we test for this. If it can be scratched by a fingernail, it might be talc. It's a 1 on the hardness scale. Okay, like I was saying, 1 is the softest and 10 is the hardest. So a 10 on the hardness scale is a diamond. 2 is also being scratched by a fingernail. And our example here is going to be gypsum. Gypsum's just a little bit harder, but it's still pretty easy to scratch. This is what's inside of drywall. So gypsum's inside of drywall. A 3 can be scratched by copper, but not scratched by your fingernail. So if you can scratch it with a penny, it's a 3 on the hardness scale. And the example is calcite, a relatively soft mineral, but getting harder. 4 can be scratched by a steel, like a nail, for example, and that would be fluorite, for example. A 5 is also scratched by steel, but just barely. Okay. Apatite is how you say the example mineral here. Okay. A 6 will scratch glass. A 6 scratches glass. Okay. You don't want to use glass to scratch something else, because you might start getting splinters and stuff. But a 6 will scratch glass. A 7 will scratch glass easily, not even hard to do. Okay, and that example is quartz. Okay, so there's only one more test we can do, and that's on level 8 here. If it'll scratch quartz, that means it's a hardness 8. That would be like a topaz. 9 and 10, there's no test for. And our examples would be corundum and diamond. So, to help make this a little easier to understand, here's how you would use this. You kind of want to go back to this when you're actually testing a mineral, but the first test you're going to do is with your fingernail. Okay? If it can be scratched by your fingernail, that means it's either a 2 or a 1. And you're done. You know that this is really soft. Okay, it's a 2 or a 1. If it scratches your fingernail, that means it's 3 or more, and you need to do more tests. So you're gonna move on down here. The second test, grab a penny. If it can be scratched by a penny, that means it's a 3 or less. If it scratches a penny, that means it's a 4 or higher. The third test is a steel nail. If it can be scratched by a steel nail, that means it's a 5 or less. But if it scratches a steel nail, that might mean it's a 5 or more. Okay. So then take your little piece of glass. You don't want to scratch it with the glass, because you're going to start getting little glass splinters everywhere. But if it scratches the glass, it will be a 6 or more. Alright, so if you're really curious, you can take some quartz out. If it can be scratched by quartz, you know it's a 7 or less, but if it can scratch quartz, it's an 8 or more. So using these tests, along with this chart up here, you can kind of get a sense of where a mineral is on this scale. You can't tell exactly where, but you can say, oh, it's definitely a 1 or a 2, or it's like a 6 or a 7. You can get within 1 or 2 of what the hardness of a mineral is. There's only one lesson left, and it's really short. That's lesson 4, luster and streak. So first of all, luster, that's how it reflects light. So for example, there's dull, metallic, vitreous. I have examples to show you right here. This right here is a dull luster. Here's a metallic luster, and here's kind of a glassy, vitreous luster. Just to give you an example of something to look for. The final thing you need to know is the streak color, and that's pretty simple. The color left on a streak plate. If you look here at this gold thing, it left a black streak. That's how you can tell the streak of the pyrite right here.